So you can see from the objectives, our goals for the end of today is that you'll be able to not only define momentum, but actually calculate it for an object. And then also we're going to learn about something called the impulse momentum theorem. And you should be able to use that theorem to determine how much force is applied to achieve a specific change in momentum. So that will make more sense as we define what impulse momentum theorem is. But it's essentially another formula for you to use.
Gotcha.
So we'll start with a scenario for you to think about because it helps pinpoint what part of motion momentum deals with. So imagine you're watching a soccer game, balls flying around the field, and a player chooses to head it towards the goal, and it comes into contact with their forehead. Both the ball's velocity and the direction are going to be changed dramatically by the collision that happens. And so far in physics, we have learned a couple of ways to describe this, right? We would describe this scenario by using kinematics equations. These kinematics equations would help us predict the one-dimensional motion of the ball. We could predict it before the collision and after the collision, right? And we could use Newton's laws of motion to calculate how the motion of the ball will change when it's struck. So now we can describe both the one-dimensional motions and the change that happens to the motion. But there's a piece left that we wouldn't be able to describe because in order to explain how the strength of the force and the duration of the force affect the collision and affect the motion, we would need to understand the concept of momentum. So that piece right there where we're talking about how long the force is applied and how strong the force is and how that affects the momentum and the motion of this object, that is the piece that deals with momentum specifically. So, momentum, the topic of the hour. Colloquially, momentum is used to refer to objects or to concepts that are picking up speed or hard to stop, right? So if you could describe a movement, like a social movement, as having momentum, generating momentum, right? A political party can have momentum in an election because we're using it to describe something that's going to pick up in popularity or grow in strength. And though this is one of those rare occasions where the colloquial definition of a word and the science definition of a word actually match up pretty decently, right? So in physics, we define linear momentum as momentum is equal to the mass of an object times its velocity. Because obviously we already have mass that's abbreviated with the letter m, we use the letter p to indicate momentum. We use m for mass and then obviously v for velocity. And as you can tell from the fact that they are bolded, momentum is a vector. So both velocity and momentum are vector quantities because if you take a scalar like mass times a vector like velocity, your final quantity will have a direction and therefore will be a vector. For momentum, the direction is just going to be the direction of the velocity of the object. So if your velocity is 10 meters per second to the north, your momentum's direction will be to the north. As we said, momentum is a vector quantity, and the direction comes from the velocity. Any change in the mass or velocity will result in a change in momentum. Usually in the problems that we are doing, we're not obviously going to have a car just change its mass halfway down the street. So usually the piece that will be changing will be the velocity. But sometimes you may be given a question where they say, here's the momentum of this object. What would the speed of a smaller object need to be in order to achieve the same momentum? So in that case, you might see a change in mass. I could have sworn I had units on here. Maybe they come later. Example problem. there's the unit in the middle of it. The unit for momentum is kilograms times meters per second. So it doesn't, it's not, unfortunately, it's not like a Newton where they gave it a new name. So we just have to clunk around and say kilograms times meters per second every time. So here's our example problem. An ostrich has a mass of 146 kilograms and it's running with this specific momentum. So you need to use that equation to calculate the velocity of the ostrich. So I'll give you a moment to do that. So to do this, we're going to use the equation momentum is equal to mass times velocity, but we're lacking velocity. That's what we want to solve for. So we'll just manipulate this to be the equation velocity is equal to momentum divided by mass. So we should be able to take the momentum, 2,480 kilograms, times meters per second, and divide it by kilograms, 146 kilograms. There's our dimensional analysis playing in, and we can see we've got the right unit, so we must be doing this problem correctly. And when we work it out, the math should come out to approximately 17.0 meters per second, and the direction to the right. Right. It's going right. Good. Moving right along then, let's talk about impulse momentum theorem. Understanding impulse momentum theorem helps to understand that changing momentum is closely related to force, because in order for something's velocity to change, there has to be a force involved, right? So the strength of the force is going to be directly connected to how much the momentum changes. And this theorem just puts that into words for us. In fact, they're so closely related that when Newton first wrote his second law, which we now know is force is equal to mass times acceleration, he actually didn't write force equals mass times acceleration. He wrote force is equal to the change in momentum divided by the change in time. So, very closely related. The rewriting of Newton's law gives us what we call the impulse momentum theorem, which can be written as force times the time interval over which that force is applied is equal to the change in momentum. Or if you want to write it out as a formula, you can pick one of these. Force is equal to change in time times change in momentum. Or to help your brain understand all the things that are involved, you can write it as force is equal to change in time, or force times change in time is equal to mass times velocity final minus mass times velocity initial, which would just be change in momentum written out. About you, but sometimes it helps me to see all of the quantities involved, whereas if I just wrote change in momentum, I might forget that mass and velocity were involved there. Impulse momentum theorem for the equation, the reason we call this impulse momentum theorem is because force times time is called the impulse of force over the time interval. So that's why we call it impulse momentum theorem. It's connecting the impulse to momentum. Impulse momentum theorem can be used to explain several different concepts. We're going to touch on each of them. It explains why, like, having good form when you are a sports player, an athlete, is important, because it allows you to maximize, like, let's say you're a volleyball player. Having the right form allows you to maximize the amount of time that your hand is in contact with the ball, thereby lowering the amount of force you have to apply in order to achieve your desired goal. So if you can maximize the amount of time that your hand is in contact with the ball, you don't have to hit it as hard to change its velocity and change its momentum the way you want it to. Whereas if you are jumping at the wrong time, or you have the wrong form, or your swing is in the wrong place, you're going to minimize the amount of time that your hand is in contact with that ball, and then you're going to have to hit it a heck of a lot harder to do what you want to do. So, large objects that are moving at high speeds require large forces to stop them, often resulting in damages to those objects because of the high forces required to stop them. Okay, so this is the first example problem that we're going to do with the impulse momentum theorem, is talking about objects that are massive and moving at high speeds. So what I would like you to do is, we have a 1,400 kilogram car. It's moving west with a velocity of 15 meters per second, and it collides with a utility pole and is brought to rest in 0.30 seconds. I want you to use the impulse momentum theorem to find the force exerted on that car during the collision. So what we're going to do is take that impulse momentum theorem, the force, oops, I went ahead a page, that's not what I wanted. There we go. Push the wrong button. Force times change in time equals the change in momentum, which we're going to write out to be mass times velocity final minus mass times velocity initial. Okay? And then we're going to manipulate this by dividing by time so that we can get force on its own. So if we do all of that, then we'll wind up with the force being equal to our mass, which is 1,400 kilograms, times that velocity final, which we know if it's brought to rest, that final velocity is 0, so meters per second, minus our 1,400 kilograms times the initial velocity, which is 15 meters per second. And then we're going to divide all of that by 0.30 seconds. So what we wind up with is about 21,000 kilograms times meters per second, which is our momentum, or our change in momentum rather, divided by 0.30 seconds, which when you do the math, the force then comes out to be 7.0 times 10 to the 4th newtons. And then because this is a vector, we need a direction, and since we know the car was moving westward, the force to stop it must have been moving in the opposite direction, so we would say to the east. All right, resuming. So these are the things we already know about impulse momentum theorem. The next thing that can be described by impulse momentum theorem is that an object's stopping distance will be different depending on its momentum. So something that has a greater momentum is going to require a longer distance to stop it. So you're going to come across problems that ask you to find stopping distance. For example, in this example problem, it says a high-speed train with a total mass of 9.25 times 10 to the 5th kilograms travels north at a speed of 220 kilometers per hour. Suppose it takes 16 seconds of constant acceleration for the train to come to rest. So that clue right there should tell us that this is, in fact, negative acceleration.
Yay.
Okay. Calculate the force acting on the train during this time, and what is the train's stopping distance? Now, I'll give you a heads up. You're going to be using the impulse momentum theorem to solve for the force, but in order to find the stopping distance, you're going to need one of our kinematics equations from the first chapter.
Okay.
So, very first thing I would do, let's convert that velocity into meters per second, because if we don't do that, it's going to mess with us. So we're going to take our 220 kilometers per hour and convert it by saying there's, in 1 kilometer, 1,000 meters, and in 1 hour, 3,600 seconds. So if we do that conversion, then we should wind up with like 61.11 meters per second. Okay, and this would still be to the north, right? Because that's the direction the train is traveling. So with our new velocity then, we can go ahead and calculate the force, same as we did in the previous problem. right? We'll just take force and we'll say that it's equal to that change in momentum, which we know the initial or the final momentum will be 0 because the train has stopped moving. So we'll say 0 minus the mass, which is that 9.25 times 10 to the 5th kilograms times our new velocity that we calculated, which would be 61.11 meters per second. And then we'll divide all of that by the change in time, which they said it took 16.0 total seconds to do that in. And we should come out with a force that is negative 3.5 times 10 to the 6th newtons, which you could, instead of writing it negative, you could just say it's 3.5 times 10 to the 6th newtons to the south. Because that's the negative just tells you it's in the opposite direction to the train's movement. Then we're going to need to find the stopping distance. To find the stopping distance, we're going to use a kinematics equation. We are solving for displacement, which we don't have, but the properties we do have are mass, velocity, initial velocity, final, and time. Now, we don't need mass for this kinematics equation. We can just as easily use the 1/2 velocity initial plus velocity final. Whoops, I wrote that instead of F, times the change in time. Because we don't have any acceleration here, but we have an initial velocity, we have a final velocity, and we have a change in time. So it should be simple enough to solve for our displacement. So then we'll just plug in our final velocity was 0, our initial velocity was 61.11 meters per second, times our change in time, which was 16 seconds. And when we multiply all of that out, we should come up with a displacement that's about 490 meters. And then we would say this displacement is to the north because that's the direction we traveled for the displacement. The final thing that we can learn from impulse momentum theorem doesn't require an example problem, but we will be doing a project on it later, which is that when the time interval over which a force acts is increased, the force required to change that momentum is less, which is the reason why if you drop an egg on a pillow, the egg does not break, but if you drop it on the ground, it does. When the egg hits the ground, the time over which its momentum changes is very short, right? It goes from moving very quickly to moving very slowly to not moving at all in a matter of seconds, right? Whereas if you put it on a pillow, because the pillow compresses, it makes that change in momentum happen over a much longer period of time. And as a result, the force that is applied to the egg is much less and is therefore not enough to break the shell of the egg. So we're going to learn a little bit more about collisions and things, but we're going to take this piece of information and what we learn later in the chapter, and at the end of this chapter, you are going to use it to design an egg drop container to attempt to save your precious egg from doom. All right.